Now, the model that we've looked at up to this point, going back up here, is that we have a single mass attached on a spring. But as I wrote up above, we want to model this for molecules where we have two masses attached via a bond. And so it turns out that the problem is actually mathematically the same, even if we have the two masses, but we have to make some slight changes to the way we define the problem. So the first change is in our coordinate x. So x in the original problem is just how much the single mass had stretched or compressed. And now x becomes the relative distance, relative separation between mass 1 and 2. So at rest, right, if the bond or our spring is at rest, we call that x equals 0. And if either side, right, either our mass 1 moves to the left or the mass 2 moves to the right, or relative to each other, they become further apart, that would be positive x. And if either side goes in, that would be negative x. Right, and so x becomes the relative separation between mass 1 and mass 2. The other thing we need to figure out is if we have two masses, we can't just model it as a single mass in terms of masses that go into our equations. And so we define what we call the reduced mass. And this is the mass as for these two particles as if they were a single particle. And we can treat them as sort of one particle having this reduced mass. And so the reduced mass is given the symbol mu, and it's defined as mass 1 times mass 2 divided by mass 1 plus mass 2. And so in all of the equations that we use for the quantum harmonic oscillator, and when we're looking at this sort of model of a molecule with two different masses, anytime we have a position that shows up, it's going to be this x, this relative separation between our two masses. Anytime a mass shows up, for example, like in the kinetic energy term of the harmonic oscillator or the Schrodinger equation, we'll use the reduced mass to give us the correct formula here, because everything needs to be relative, right? These need to be relative values. So if we go ahead and do that, our Schrodinger equation becomes negative h bar squared over 2 mu. And then we'll have our second derivative with respect to x. And again, x is defined the way we've done it here. And then we add the potential energy, 1/2 k x squared. And so this is the Hamiltonian operator for the harmonic oscillator. Now, one thing I haven't mentioned yet is what does this x represent, right? We call this this is sometimes called the Hooke's law constant, or commonly also the force constant. And what this is a measure of how stiff a spring is, or how strong that spring is. So the larger k is, the stronger the bond in the molecule, and the smaller k is, the weaker it is. And so that sets up our problem, right? That sets up our problem in terms of reduced mass and in terms of the relative separation between our masses in our molecule.